Hello viewers of mine, this is another What the Physics video on circular motion. We're going to be talking about centripetal versus centrifugal forces, as well as everyday applications. But before we do that, we need to summarize tangential velocity, centripetal acceleration, and centripetal force. Just a reminder what these words are, the ones that I'm saying, tangential and centripetal. Tangential touches the curve just once, and it's going to be perpendicular to the radius. Meanwhile, centripetal, that is center-seeking, center-seeking, and that's going to be parallel to the radius. So which one goes with which? Well, it says it right up here. The velocity is the one that's tangential, and the acceleration and force, those are the ones that are centripetal. So that means the velocity is always going to be perpendicular to the acceleration and the force, at least for uniform circular motion. It gets a little more complicated than that if you move on to take more advanced physics, but that's good for right now. That's why the object that is going around is not speeding up or slowing down. Then there's, of course, equations for tangential velocity, centripetal acceleration, and centripetal force. I'll let you go back and check those out yourselves and write them down. And then we also learn about the path the object takes when the centripetal force is there and is not. And that has to do with inertia when it's not there. And actually that's going to come into play a little bit here when we deal with the centripetal versus centrifugal. Ooh, good stuff. Nice segue. And finally, what are the forces that cause circular motion? So sometimes it's just one force, sometimes it's a combination of forces. But yeah, it's important that we know centripetal force is not its own force, that there is one or more forces that work to cause this circular motion. So that's the summary stuff. Let's go ahead and move on to the new stuff with the learning targets. So I can distinguish centripetal from centrifugal and see how it is inertia that affects objects in a turning vehicle. And I can apply circular motion concepts to everyday situations. Oh yeah, it's physics. Here's an everyday situation. Going to Panera. Oh yeah. Let's say you're driving back from Panera with your soup, your sandwich, your soda, and you take a hard right turn. What happens to the food and anyone else in the car that is in the passenger seat? You notice all of a sudden the food starts going somewhere. What's going on? What's going on? It starts to spill. Oh no. Okay. You feel yourself pushed into the door and the food slides as well. So you say, there's some force acting on it because I'm pushed into the door, right? Kind of, sort of. This happens because of inertia. Now, if you remember the oatmeal situation, that was when I foolishly put a Tupperware of oatmeal onto the top of my car and drove off to school. And then when I got to school, I realized, oh no, my oatmeal. I put it on top of my car and I never put it into my seat. And then, of course, I looked and, yeah, the oatmeal was not there. And then on the way home, I looked and found where the oatmeal was. And it came off at the first turn because of inertia. Inertia means the object is going to want to keep doing what it's been doing. And that's exactly what's happening with your Panera as well. The car is turning because there's a net outside force acting on the car. But the object, in this earlier case, the oatmeal, or in this case right now, the Panera, just wants to keep doing what it's been doing. It's going to continue on in the same velocity as before. And that's what we're able to see. So if we are looking at it from like an above view and we could somehow see inside the car, and this is supposed to be the food, you see as the car is turning out to the right, you see the food or whatever, oatmeal, Panera, person, is continuing in a nice straight line until what happens? It seems like the car door runs into the person or food or whatever. And what is truly happening is the food or the object is just continuing in a nice straight line. That's inertia. Okay, it seems like that we're being pulled out, but that's from inside point of view. Okay, so like, oh yeah, yeah, that's centrifugal force. First of all, let's be careful when we say centripetal versus centrifugal. So for this comparison, I'm going to say centripetal and centrifugal, just to make sure that we're distinguishing, because they're super similar sounding. So what's centrifugal? Well, that's from the point of view from inside the car. As far as you know, you're just driving along. You don't really know. Let's say you're the passenger. You don't realize that the car is turning. All you realize is suddenly there is some force pushing you up against the door. And you say, oh, this is the centrifugal force. Well, so is that real or is this not? Well, it is actually real. A lot of people say, no, it's not real. It's real, but the system that you have to look at, the frame of reference is super duper complicated, way more complicated than we're going to deal with here. So as far as we're concerned, yeah, you can say the F in centrifugal force is standing for false force. When you go on to take more advanced levels of physics, we'd say, oh yeah, okay, centrifugal force is real, but it's just some hardcore frames of reference because there's inertial frames of reference and non-inertial frames of reference. Anyhow, this is what you would be seeing from inside the car's point of view. All of a sudden, you're just kind of moving to the side. Okay, we just talked about it on the previous slide and how we're going to be applying it here. That is inertia. The object is going to keep going in the same direction it's been going, and it's because of inertia, and it's the car that is going out from under it. If you go on to take more fancy pants advanced physics, we can learn more about the centrifugal force. But right now, we're just going to consider the centrifugal force to be fictitious force. Okay, good stuff. This also applies, by the way, when you are talking about spinning stuff around, and if you're like trying to get the water off of things, like if you have an upright washing machine, if you notice that the spin cycle doesn't exactly dry out the clothes, as in they're not warm like from the dryer, but it does help to get rid of all the clothes, the water on the clothes, because spin, 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 the clothes end up toward the outer edge of the washing machine's tub, and the water is able to go out the little holes in the tub. Okay, if also you have one of those spinning salad cleaners, you rinse off the salad and you say, oh, the salad is all wet, so you put it in one of these things, spin, 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 and all the water goes out. The water is going out because of inertia. It's not going out because of some force. Man, it's physics. It's physics. All right, let's talk some more stuff about everyday applications beyond washing your clothes and rinsing off your lettuce before you eat your salad. Driving applications. So why is it that we have to slow down when we're going around curves? Well, we know when we're going around a curve, we are already accelerating, right? Because of the circular motion, that's centripetal acceleration. But when I'm saying accelerating here, I mean we're going to be slowing down. So why is it that we have to slow down? We might be going along at 40 miles an hour, 30, 20, and so on. Okay, so if we're going around here, we're going to turn right. Let's just say we have this force that is causing us to go to the right, and that force is going to be friction. We've discussed that several times already. So how does the required turning force from the friction compare to the velocity? As in, how big does each one need to be? Well, as we had talked before and as we had demonstrated before, when I had the turntable and I had the pennies on the turntable, spin, 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 they're going around, and the pennies that were going the fastest were farther out to the edge, the ones with the largest radius. Okay, so we saw, okay, the ones with the farthest from the center, the closest to the edge, largest radius, therefore the largest tangential velocity, and they needed a lot more friction to stay in place than the pennies closer in. So you say, okay, yeah, sure. So that means that should apply here too, right? When we're going around a curve, that should be a similar effect on the radius, right? Well, kind of different. We do recognize that we need to slow down on the turn, but it turns out, oh goodness, as it so happens, if there's not enough friction, what you want to do is actually have a larger radius for the turn. You say, wait, what? Let's go through it. So we can reduce the necessary friction by slowing down, but a lot of people don't really like to slow down. So what other ways can they do it? What can road engineers do in order to figure out, hey, these people want to be going fast as they exit off of the interstate or as they go onto the interstate? How can we make it safe for them? Okay, so the radius of the exit ramp, and this is pretty cool stuff. Increasing the radius but keeping everything else the same will actually decrease the required centripetal force. As we said, the frictional force that is necessary. So centripetal force is inversely proportional to the radius. Now you say, wait, whoa, what? The physics is going on here, Fair. You just said on the previous slide that increasing the radius would increase the centripetal force. And yes, and notice what I said was that was for the little turntable. That was for the turntable. That was for objects going around on a spinning rigid object. In other words, that's when we had a constant angular velocity. And the farther out we were, we had a larger tangential velocity. In this case, what we're talking about here, if we have the exit ramp with a larger radius, we have a set tangential velocity. So a larger radius does not increase the tangential velocity. We're assuming a set tangential velocity. So that means increasing the radius will actually decrease the required force. Physics. Now, other things we can do would be banking curves. That would allow for gravity to help keep you on the road. So as you can see, the car is going around this curve. There is a bit of a tilt, and that the gravity is actually helping, oh, go away, lines. The gravity is actually helping kind of pull the cars downwards into the turn. So if the cars end up going too slowly, they will go right down into the center area. Not likely to go that slowly, of course. Now, this is going to be very, very important when we're talking about bad weather conditions, snow, ice, and so on. But yeah, that's very, very applicable for us. You say, okay, yeah, sure, I suppose, but really, is that something that I need to worry about? Because I'm not going to be designing any roads. Okay, this is also applicable when we're doing fun stuff like going on one of these rides. We're going along on these rides, and we don't want a whole lot of friction on these water rides. Are you kidding me? That is not very comfortable at all. So we cut down on the friction by having the water slide going along, and we are riding on top of the water, right? So there's essentially going to be zilch on the friction. So how is it that we make the turn? If there's no friction to help us make the turn, that is a very short ride as we fall right off into the parking lot of the amusement park. That's not very nice. So what they have is they have this wall here, and as you can see, the wall is going to be a normal force that is going to be pushing in on the occupants of this inflatable here. Oh, okay. It's actually a very, very similar thing to when we're talking about the Winter Olympics and like toboggans and stuff like that. They go around and they use the normal force to help actually reduce the frictional force to help make them take turns a lot faster. And finally, we also see it, once again, more everyday situation than Winter Olympics, I suppose. When bikers go around curves, they are leaning into the curves, whether we're talking about motorcycles or bicycles, do a similar thing. And finally, my last application isn't exactly an everyday sport, but it's still pretty darn cool. It's the hammer throw. So the hammer throw, First of all, it's not like you pick up a carpenter's hammer and just start throwing them. That would be silly. That'd be silly. We're talking about a giant rock on the end of a large rope. Okay? That's what a hammer is. Silly. No. Okay, so this originated in the British Isles, dating back thousands of years. This is still popular in the Highland Games. If you've ever been to the Highland Games and you've seen a bunch of really jacked people going around in kilts and just like picking up literally like the caber toss, looks like giant telephone poles, and they toss them up in the air. Or they pick up giant boulders and they try to throw them for distance. Well, this right here is going to be the hammer throw. So a hammer throw, or the hammer, is a big heavy ball. So 16 pounds. It's essentially a big sized bowling ball on the end of a cord. It's approximately 4 feet long. The competitor spins it around several times, picks up speed, and then they release it at just the right time, and it goes as far as possible. This is using circular motion. They can get the tangential speed nice and really, really big by increasing their angular speed. Now, there's also tricks you can do with, keep in mind how the kinetic energy and gravitational potential energy are going back and forth. But what's super impressive is record distance is over 86 meters, which is just 15 feet shy of a football field. So I can't even pick up a baseball and throw it the length of a football field. Try doing that with a bowling ball. That's just, yeah. There's some seriously cool applications of physics here.